Our next speaker is Jon Grantham, and he will talk about extremely pointless curves.
Thank you very much, and thank you to the organizers. I have been to the Maine Quebec Number Theory Conference before, but this is my first time at the Quebec-Maine one, which I've always wanted to do because I've always wanted to see Quebec City, so that is still on the list. In lieu of that, I have another beautiful part of Canada behind me. So welcome to my extremely pointless talk. This is about extremely pointless curves, and this is continuing work, as you'll certainly see by the last slide, and it is with my colleague Xander Faber. So to define extremely pointless curves, I need to talk about the concept of gonality. If you came late to arithmetic geometry like I did, you'll need this defined for you. The gonality gamma of a curve K, or curve X, excuse me, over a field K is the minimum degree of a non-constant K morphism X to the projective line. And what does this look like for some fairly straightforward curves? So gonality 1 says essentially there's an isomorphism there. So curves that are isomorphic with the projective line are genus 0 curves. And gonality 2 curves, there's a 2 cover which corresponds to hyperelliptic curves, and you can specialize that to elliptic curves. So those are genus 1 and up. And gonality 3 curves are known as trigonal curves, and I believe the word gonality was a back formation from the term trigonal. So, and just assume for the rest of this talk that I've defined curve to answer the question you're about to ask me about, is it smooth, etc. So one question to explore, and Van der Geer asked this question, is that given a smooth projective curve over a particular finite field Q that has genus G and gonality gamma, what is the most number of points you can have? So if you compress this question and leave out the gonality, you can look at, for example, manypoints.org has sort of a table of the best known bounds for a lot of different Q's and G's. And indeed, Van der Geer was one of the first to construct such a table. And the question is, what happens when you filter by gonality gamma? So we looked at relatively small genus curves over binary, ternary, and quaternary fields in previous work, but this and there was some of them you could make an argument, and some of them you just wanted to do a computer search, hopefully in a clever way, as not to take too much work. And but this led us to this question that I'm going to talk about today, and this definition of pointless curves. So there's this upper bound on the gonality over a finite field. The upper bound is G plus 1, and but it's almost always G, because if the curve has a rational point, then the gonality can't be G plus 1. It has to be G or lower, and therefore we refer to a curve without any rational points as a pointless curve. And Howe, Lauder, and Top wrote a paper that introduced this concept and explored it. But these are even stranger than curves without any points. If you can show that if it has gonality G plus 1, then it has no effective divisor of degree G minus 2. And that implies it has no points over these various extension fields of FQ. So since it's pointless not just over the base field, but also over several extension fields, we coined the term extremely pointless curves to refer to these. And so the question is, when can these occur? And the Weil bounds give you a particularly straightforward derivation that for a particular genus, you can bound this as a function of the genus, and this is a decreasing function. So you have a finite list of possibilities for Q's and G's. Just from this bound alone, there's a fair number of cases to consider for G equals 3, 4, 5, and 6, a lot fewer, and 7 through 10, you're only looking at binary curves, and beyond 10, there aren't any. So when we entered this, some of this was known and some of it wasn't. The previous results, so Howell, Lauder, and Top in their original paper classified all, well, they didn't call them extremely pointless curves, but it corresponds to plane quartic. So there are only certain of those cases that are possible. So in particular, 25, 27, and 31 get ruled out by their work. And in our previous work, we found one of genus 4 over F2. Kastrick and Tutman had previously found one of genus 4, a ternary curve. And through exhaustion, we were able to show that over F4, you can't get a genus 4 gonality 5 curve. And we also ruled out the case of genus 5 gonality 6. And if you want to see more detail on this, the preprint of the binary work is on the archive, and the ternary and quaternary curves, that's almost finished. We'll post that hopefully in the next week or two. If you want to hear me talk about it because you haven't gotten enough of binary and ternary curves, earlier this year I gave a talk at the Number Theory Online conference hosted by Karma at the University of Newcastle. That talk is available on Vimeo. So what is left after we've considered this? So we have had 8 cases left. For genus 4 curves, our previous work only considered binary, ternary, and quaternary. And for genus 6 is something we didn't go up to. And then you have the binary curves over with genus 7, 8, 9, and 10. So here's where we employed a different technique than the ones we used in our original work. In particular, Lauder's, what we call Lauder's algorithm for Serre's explicit method. So Serre gave a way of ruling out particular types of curves over finite fields, but I think what we decided on is to call what Serre had a technique, and what Lauder turned that into an algorithm. So you can compute a list of all possible zeta functions of a curve over a finite field. And for an extremely pointless curve, you've got a lot of conditions by the terms that have to be 0, and you can eliminate most of the zeta functions. And so for 5 of those pairs, using Lauder's algorithm eliminates all of those zeta functions. So that leaves us with 3 cases to consider. And it looks like my talk is coming in much shorter than I anticipated, but I'm sure you all will enjoy the break. So that leaves us with 3 cases, and there were zeta functions that survive. You will notice that there are there's some last minute scribbling in here. Between the time I wrote this talk and today, Xander came up with an idea that for the genus 6 case realizes these curves as singular septics, and it turns out that exhausting over those is not so painful. Well, it's not painless, but it's not extremely painful either, and it's I think on the order of a day's worth of computation to show that you can't have any genus 6 curves of gonality 7, and you essentially, what you do there is that you look at these septics, and by first of all knowing that the singularities that you need to achieve to be genus 6 rules out a bunch of them, and then the extremely pointless conditions rule out even more, and then it's just a magma computation of the genus for the ones that follow. For genus 7, I think we're going to look at that later this week. That is a little bit more ambitious, and I have not really allowed myself to think too much about the genus 9 case yet. So at this point, I will stop. I will ask for questions, or in particular, if someone wants to suggest a straightforward technique for handling the genus 7 and genus 9 case, I'm all ears. So thank you.
Thank you.